Assalamu alaikum. Hello everyone. I am Abdeslam Jakjoud. I am the CTO of Teradoxa. I'm here today to talk to you about quantum technologies in their three aspects: security, communication, and metrology. So, without any delay, I'll start my presentation. I'm going to share my screen. So, our presentation today will follow the following agenda. So we'll start by talking about giving a little introduction, and then talking about quantum technologies in general, and specifically concentrating on quantum computing, quantum cryptography, and code breaking. Before talking about quantum sensors and giving some conclusions to what we are going to see today. But before our introduction, who we are. Teradoxa is a French consulting company created in 2019. Its main focus is on security and digital identity issues. It's tackling the issues of digital sovereignty of nations and societies, and it performs research and development projects in different domains such as blockchain, enterprise architectures, systems engineering, and quantum metrology. We recently published a patent about a self-validating blockchain network, including the validation mechanism, the integrity checking mechanisms, as well as the ability to, as well as our own consensus protocol. Teradoxa was founded by two people. So Emmanuel Pesenti is an enterprise architect specialized in software engineering, as well as in certified as a TOGAF architect, and myself, an R&D manager as well as CTO. I am a certified cloud architect. I have a PhD in artificial intelligence and computer science. So let's start talking about the main subject today. Quantum technologies. It's derived directly from quantum physics, which is the study of the behavior of matter and energy at the atomic and subatomic scale. The world of quantum physics is fundamentally different from the classical world, which means that its mechanism cannot be fully grasped by human intuition. There are three main concepts of vital importance in quantum physics. They are the wave particle duality, that we're going to say just in a couple of slides, the superposition, and what we call the entanglement. So, let's consider the following experiment. We have a light source and two slits with a screen. We once we project light directly to on the double slits, what we see is a phenomenon of interference, which means that we have multiple slides on the multiple illumination spots on the screen. What this means, it means that light is going through both slits at the same time, and it's causing interference, which generates the different spots, light spots and dark spots on the screen. Okay, so this is typically the behavior of waves. What we also noticed is that when we repeat the same experiment using electrons, what we see is that electrons are replicating the same phenomenon, which means that electrons are behaving like waves. We have a concentration of spots where electrons arrive that are similar to the interference behavior. So what we did is that we started sending one electron at a time, and we still observed the same thing, which means that somehow this electron is going through the both slits at the same time. which is weird. So what we did is that we positioned a detector behind the slits. And once we did that, we started seeing just one spot. The conclusion is that the fact of observing subatomic particles changes their states, obligating them to do what we call to break down to one of the states. So here what we have is that there is a duality in the state of of matter between wave and particles. At the same time, the fact that we are observing something, it pushes it to materialize, to take a state, a specific state. So these are two of the three phenomena that I talked about. There is the duality, and there is also the superposition, which means that the fact that the particle or the object or the matter is in a superposition of multiple states until it is observed. We'll talk about entanglement in a later slide. So let's go back to our main subject, which is quantum technologies. Quantum technologies have the potential to revolutionize the fields of security and communication. Traditional methods of encryption and communication are vulnerable to hacking and interception, because of the fact that if we have a strong enough machine, we can tackle the problem that is the basis of encryption, trying to break down or even use brute force attack to decode the different messages. Quantum computing and cryptography and sensors and other quantum technologies are being developed for a range of applications in these two fields, communication and security. So let's start by talking about quantum computing. Quantum computing is a fundamentally different kind of building computers. It's based on using quantum mechanical phenomena to perform operations on data. What we use in classical computing is the representation of information through two states, 0 and 1. So what we do in quantum computing is that we use two kind of vectors, what we call a ket. It's the 0 ket and the 1 ket that you see on this slide. And they are representing two states of matter. And given that we have the possibility to have a superposition, it means that our particle representing the qubits can be in a superposition of 0 and 1. You can refer to a previous conference I did at the same school. It is on YouTube currently, that tackles this problem in more depth. So, uh, in contrast to classical computing, which uses bits that can be either 0 and 1, our qubits can be a composition or a superposition of both these states. This allows quantum computers to perform certain operations much faster than the classical computers, especially in problems that involve searching large databases or factorizing large numbers, what we call the Shor's algorithm. However, many researchers and companies are working on developing quantum hardware and software. There have been some impressive demonstration of quantum algorithms for specific problems, such as breaking classical encryption, designing new quantum resistant encryption methods, and simulating complex quantum systems for drug discovery and material science. So, why should we care? The market for quantum computing is still in its early stage, but it's expected to grow rapidly. According to a report by Marketing Markets, the global quantum computing market is projected to grow from 472 million in 2021 to 1.7 billion by 26. So this is a huge growth in in an early bird market, and it's being driven by the growth. This growth is being driven by a combination of multiple factors. So we have the need for faster and more powerful computing to solve complex problems in areas such as drug discovery, financial modeling, cryptography, logistics. The increasing availability of quantum hardware and software from companies such as IBM, Google, Microsoft, AWS, and the growing interest from governments and research institutions in developing quantum technologies for national security and scientific research. The market is still dominated by hardware, such as how to build quantum processors, but software and services are also expected to grow in importance. As a matter of fact, there is a lot of interest in what we call the quantum machine learning, which is specifically a software aspect of the technology. The market is also segmented by application, with areas such as cryptography, simulation, optimization, machine learning expected to be key drivers of this growth. Challenges to the growth of the market include the high cost and complexity of quantum hardware, such as sorry, as well as the need for specialized expertise in quantum computing and a good knowledge of quantum mechanics. Despite these challenges, the market of quantum computing is expected to continue growing rapidly in the coming decades. Sorry. So, let's talk about quantum computing and security. So, quantum computing has the potential to revolutionize the field of security, particularly in areas such as encryption and decryption. Traditional encryption methods are relying on hard to solve mathematical problems such as RSA and AES. They are vulnerable to attacks from quantum computers. There is what we know as the Shor algorithms that can be used to factor large numbers and can break RSA encryption. Grover's algorithm, on the other hand, can speed up the brute force attacks. It's an algorithm that was built to search in an unsorted in a very quick time an unsorted database. This means that quantum resistant encryption methods are needed to secure data against future attacks from quantum computers. One promising approach is what we call the lattice based cryptography. Lattice based cryptography is not based on algebra or number theory, but rather on geometry. It's a really elegant way to perform encryption, and it includes symmetric and asymmetric encryption. Quantum computing can also be used for code breaking, which has important implications for national security and intelligence gathering. In addition to encryption and decryption, quantum computing has potential application in other areas of security, such as quantum random number generation, which can offer us better or truly random numbers for use in cryptographic protocols. What we call quantum key distribution, that are going to see in more details, which uses the principle of quantum mechanics to distribute key encryption keys securely, and quantum sensors that can detect and measure signals with unprecedented accuracy and sensitivity, enabling new applications in areas such as surveillance and threat detection. So, let's talk about quantum cryptography and code breaking. So, as we said, unlike traditional cryptographic methods which rely on mathematical algorithms, quantum cryptography uses the specific laws of physics to ensure security of communication. The most widely known methods of quantum cryptography is what we call quantum key distribution, QKD, which allows two parties to generate a shared secret that can be used for secret communication. QKD is based on the principle of quantum entanglement, which allows two particles to become correlated in a way that is impossible to replicate with classical communication. The parties use a series of quantum states, such as polarized photons, that I'm going to explain later, to create the shared key, and any attempt to intercept or measure the key would introduce errors that can be detected. Other methods of quantum cryptography includes quantum digital signature, which can be used to verify authenticity of messages, and quantum coin flipping, which can be used to resolve disputes between parties without the need of a trusted third-way party. So, let's talk for a bit about quantum key distribution. What you see on the screen is a schema representing how this is going to be done. So, we'll start by the middle section. What we have is a light source at the bottom, and this light source is providing us with photons that go through what we call a polarizing crystal. So you can think of it as a prism that creates two streams of photons that are what we call entangles. So to simplify, entanglement means that we have two particles that are sharing an invisible bond. If I act on one particle, the other one will be updated simultaneously, which means that it's not fast, it's simultaneous. Which means that if I have once the stream goes through the polarizing crystal, both photons will share different polarization, which means that if one of the photons is horizontally polarized, the other one will be vertically polarized. So what I do is that we transmit both photon streams through two transmitters to our two parties. This is for a peer-to-peer communication. Alice, the sender of the message, will receive the first stream and will perform decoding. So decoding will be based on polarization, which means that if I have a vertically polarized photon, I will put one. If I have a horizontally polarized photon, I'll put zero, which will result in a key, in a binary key, a set of zeros and ones. I will use this key in an encryption algorithm to encrypt my message and send it through a classical communication channel. On the other side, I have Bob that will receive the other stream and will use a similar decoder, but in this case, it will invert the way it reads the different phases, because if we the different polarizations, if we have a vertically polarized photon, we will put down zero, if not one. So this is an oversimplification. The mechanism behind doesn't use just vertical or horizontal polarizations. There are also diagonal. But the bottom of the question is that we have a way to distribute the same key to two different people. So you're going to ask me, how is this more secure than what we have now? Let's suppose that we have someone who's listening, who's trying to intercept the key distribution. If you recall what I said at the beginning in the double slit experiment, if you observe a particle, it alters its state. Which means that if I am going to listen on Alice's channel, I will alter the state of the key. Same thing for Bob, which means that it will over eavesdropping will result in two different keys for both parties. So the protocol is as follows. Once we have the keys, what we will perform is that Alice will send a token, a known token, to check if there is anyone eavesdropping. It will send, she will send, for instance, hi. If no one is eavesdropping, we have the same keys. Decryption will result in hi. It means that yes, nobody else has this key. We can communicate securely. But if the someone was eavesdropping, it means that they have different keys, which means that our high is going to be decrypted and gives gibberish, which means that we should change our channel. We should check for eavesdropping. There is someone in the middle that is trying to intercept the key distribution, and this is, in a nutshell, the principle of quantum key distribution. So, the advantages of cryptography of quantum cryptography over classical cryptography is the unconditional security. When we are talking about classical cryptography, we are using some hard to compute problems so that we can prevent people from breaking our keys. But the issue is that if we have a strong enough computer, how much time it will take us to break it. Now, in quantum cryptography, we are talking about the fact that in order for us to break this kind of cryptography, we need to break the laws of the universe, which is basically impossible. So, there is also the detection of the eavesdropping and our ability to securely distribute keys. It's future proof because of the fact that we cannot break it unless we change our current universe. It will allow secure authentication and and provide us with better privacy. It can provide a high level of privacy for communications, as communications guaranteed to be secure and private from eavesdropping. But we still need to talk about the limitation. So there are some practical limitations to this approach. It's the current implementation of quantum cryptography are limited by technological challenges, such as the distance over which quantum states can be reliably transmitted and the rate at which they can be generated. Why? Because of the fact that when you have some particles that are in what we call a superposition of states, what happens is that they cannot maintain this state for a long time. They need to go to a specific state, which means that this is just a practical limitation for the time being. It reduces the distance over which we can hold these quantum states, and it prevents us from having a widely distribution of our systems. So the cost of implementing cryptography is currently very high due to the need for specialized equipment and expertise. As you saw, we used a specific transmitter and a specific receiver because of the fact that we are using, for now, we are using laser beams for the communication of the different photons. And we also rely on what we call the classical infrastructure. Despite the use of quantum states, quantum cryptography still relies on classical infrastructure to perform communication, which result in what we call the potential for side channel attacks, which means that if an attacker goes and attacks the side of the system that is classical, not quantum based, if they find a vulnerability in that system, it makes the whole quest to secure the message smooth. So now let's talk a little about code breaking. Many classical cryptographic methods, such as the widely used RSA encryption, rely on the computational difficulty for certain mathematical problems, such as factoring large numbers or computing discrete logarithms. Quantum computing has shown a huge potential to solve these problems much faster than classical computers using algorithms such as Shor's algorithm. It can factor large numbers and break RSA encryption in polynomial time, rendering many current cryptographic methods vulnerable to attack. While the practical implementation of Shor's algorithm on a large scale quantum computer is still a challenge, the potential for quantum code breaking has led to significant research into post quantum cryptography, which aims to develop new cryptographic methods that are resistant to attacks from quantum computers. Post quantum cryptography includes methods such as the lattice based cryptography, and I recommend that you take a look at this method. It's extremely elegant and beautiful, and hash based cryptography, which rely on mathematical problems that are believed to be hard to crack even for quantum computers. Let's have just one precision about what are quantum networks. When we hear the word quantum network, they are some networks that are built using combination of quantum and classical hardware and software, including quantum computers, quantum communication devices, and classical communication channels. As we saw earlier, we used a quantum device to share the key, so for the quantum key distribution, but we used a classical communication channel to send our encrypted messages. So that was a basic quantum network that we built. Quantum networks have potential to enable secure communication and computation in a wide range of fields, including finance, healthcare, and national security. One example of quantum network is the quantum key distribution that we saw, which uses quantum communication to distribute encryption keys, but classical communication channels to drive the messages. There is some talk about what we call quantum internet. It's a proposed network that would enable secure communication and computation between quantum computers all over the world. Quantum networks face many challenges, including the need for high quality quantum hardware and the development of reliable quantum communication devices, as well as the management of quantum states to avoid errors in what we call decoherence. Decoherence is when you have this particle that represents, for instance, your qubit that needs to collapse into one of the states. So it means that your time of calculation is extremely reduced. Let's talk about where the money is right now, what we call quantum sensors. So, quantum sensors are type of sensors that use the principle of quantum mechanics to detect extremely weak signals with high precision. Traditionally, sensors rely on classical physics and are limited in their sensitivity by the uncertainty principle. Uncertainty principle is a principle that was introduced by Heisenberg in the beginning of the 20th century, and it says that we cannot know with 100% certainty the position as well as the speed of a particle. Quantum sensors, on the other hand, use the principle of quantum mechanics such as entanglement, superposition to overcome these limitations and achieve high sensitivity. They can be used to detect a wide range of signals, including gravitational waves. They are currently in implementation to improve how we detect gravitational waves, magnetic fields, and chemical molecules. One example of quantum sensors is what we call the atomic magnetometer. It uses the spin of atoms or electrons to detect magnetic fields with high precision. For instance, I don't know if you know that there are some birds that travel by night, and that are able to find their way while migrating. For instance, the robin, I think it goes from Sweden to Spain every year without getting lost. So how they do it? It is believed that the robins are using some kind of quantum entanglement mechanisms to build a basic or a natural quantum magnetometer in their eyes. What they use is that there is this molecule, this protein called the cryptochromatom, that is, when broken down, it will give two different molecules with one radical electron. This electron will have a spin up or a spin down, and in the presence of a magnetic field, one of the electrons will change its spin, which means that if the same molecule can go back to the same state, it means that there is an absence of magnetic field. If not, it means that there is a magnetic field on that point. So basically, they use it to feel or to sense the strength of Earth's magnetic field, and thus building a kind of classical of positioning system that does not rely on any external device, so that they can orient themselves on the planet. There is another example of what we call the optical cavity sensor. It uses interference of light waves to detect changes in refractive index and can be used to detect small changes in pressure or temperature. And these quantum sensors have many potential application in different fields such as medicine, environmental monitoring, national security, where their ability to detect extremely weak signals with high precision can provide valuable insights and information. Let's talk about a very specific case of quantum sensors, what we call the quantum radar. What you see here is a big oversimplification of a quantum radar. What a quantum radar does is that it creates a pair of entangled photons. Okay, so it will send the first one for the detection, which means that it's the one that is going to collide with an airplane. In this case, I think it's an F-16 fighter. In the other one, we will keep it. We will just check it in an interferometer, in a way, in a double slit experiment. Okay, so why is this interesting? If you remember, I told you that if we act on one of the photons, the other one is updated directly, which means that if the first photon keeps going, doesn't meet any obstacle, the second photon that will be in the will present an interference pattern, will project an interference pattern. But if the first one is observed, it collides with an object, the second one will just show a spot. Why is this interesting? It is interesting because we can measure the second one immediately after we separate them. And once we measure it, we will know what will happen in the future. It means that with up to three devices of this kind, we can know if there is an airplane and where the airplane is going to be, not where it is right now, where it is going to be, because of the fact that we are measuring it right now, in that in that it acts directly. It's as if there is a signal that goes through time to prevent to tell us if there will be any object that will collide with the first photon. I know that this is counterintuitive, but please, I need to remind you that quantum physics is counterintuitive. It's not something that you can express simply using the natural language. So, as someone told me about what we call the Copenhagen interpretation of quantum physics, it is simple. You need to shut up and trust the maths. Oh. What we call an application of quantum metrology is that what I just said. So we have quantum sensors that have the potential to revolutionize the field of security, as we saw, the field of safety also. We have quantum sensors that have many advantages over traditional sensors, including higher sensitivity and precision, as it was in the case of the robin that can navigate the Earth without getting lost, and the ability to detect signals that are way too weak or too small to be detected by traditional sensors. So, as a conclusion, quantum technologies have the potential to revolutionize the fields of computing, communication, and sensing, but they also pose significant security risks that must be addressed. While much attention has been focused on the threat of quantum computers breaking classical encryption schemes, quantum sensors and quantum cryptography may actually be an easier target for attackers. Quantum sensors are vulnerable to attacks that involve manipulating the weak signals they detect, while quantum cryptography is vulnerable to attacks that exploit the weakness in the hardware or protocols used to transmit the quantum signals. Protecting against these types of attacks requires a combination of hardware and software security measures, as well as ongoing research and development to improve the security of quantum technologies. While the development of quantum technology is still in early stages, it is important to begin considering the security implications of these technologies now, so that we can develop robust and secure systems for the future. As we continue to develop and deploy quantum technologies, we must also work to ensure that they are used for the benefit of society while minimizing the risks of unintended consequences or malicious use. In conclusion, Quantum sensors and quantum cryptography may be an easier target than a full quantum computer, and addressing their security vulnerabilities will be crucial for the successful adoption and deployment of quantum technologies in the coming years. I thank you for your patience with me. I know the subject is kind of boring, and I'm welcoming any questions from your side.
Merci Monsieur Jacques Jeud. Alors du coup, alors personnellement, j'ai plusieurs questions.
Oui,
La première est par rapport à l'aspect cryptographique en fait.
oui.
De ce que j'ai compris, c'est basé plus ou moins sur le fait que le receveur et l'envoyeur ont la technologie quantique.
Exactement,
Mais
oui.
la question c'est, est-ce que si le hacker possède la technologie quantique, est-ce que la cryptographie quantique pourra toujours être aussi efficace que présentée par exemple? Et la deuxième question, c'est par rapport à la cryptographie justement, est-ce qu'elle est numérique? Parce que le problème, c'est que la technologie quantique avance rapidement et augmente les capacités de calcul. Ça veut dire que si on se base au niveau du long terme par rapport à la capacité de calcul,
Mhm.
elle deviendra vite obsolète.
Alors, pour les deux questions, donc je vais commencer par la première. Alors, l'élément fondamental dans la cryptographie quantique, il vient pas du fait que c'est puissant du point de vue calcul, mais que c'est puissant du point de vue nature physique. Pourquoi? Parce que supposons que vous êtes deux à communiquer à communiquer, à distribuer la clé en utilisant la technologie de la quantum key distribution. Et que moi, je suis quelqu'un de malicieux qui dispose de la même technologie. Donc, qu'est-ce que je dois faire? Je dois pirater le flux de distribution de la clé pour pouvoir connaître ce que vous dites. Par contre, même avec la même technologie, si je lis le flux, ce qui arrive, c'est que je suis en train de l'altérer. Parce que c'est fondamental, quand on observe une particule au niveau subatomique, on altère son état. Ça signifie quoi? Ça signifie que le flux qui passe à gauche est fondamentalement différent du flux qui passe à droite, qui va donner comme résultat deux clés différentes. Donc quand vous allez essayer de communiquer, vous allez vous rendre compte rapidement que ça ne passe pas, que l'un des flux a été compromis. Donc il y a une sorte de détection, d'intrusion, avant même la communication du message utile. Est-ce que c'est clair?
Oui, plus ou moins. Mais du coup, ça veut dire qu'ils vont changer de canal à partir du moment qu'ils détectent la moindre variation, c'est ça?
Exactement, ils vont changer de canal ou vont relâcher les chiens de guerre parce que vu la distance sur laquelle en fait la transmission se passe, ça signifie que je suis tout près. Et étant donné mes performances athlétiques, je vais pas courir très loin.
Ah, je valide. Mais du coup, supposons que ça devient beaucoup plus vaste en fait, à l'échelle mondiale. Ça voudrait dire que cet aspect-là risque d'être compromis, non?
Alors, l'élément fondamental qu'il faut retenir, c'est que le modèle que j'ai présenté, c'est un modèle peer-to-peer. C'est un modèle qui permet la communication entre deux points. C'est pour cela qu'on fait la distribution et on envoie les deux photons des deux côtés. Donc, il faut tenir ça en considération et que ce qu'on appelle le phénomène des réseaux quantiques est un phénomène qui est assez récent, qui est assez jeune. Donc, on n'a pas encore la capacité ni les dispositifs nécessaires pour pouvoir construire quelque chose d'aussi large, quelque chose qui va permettre par la suite de distribuer en fait une clé qui va permettre d'effectuer le chiffrement, déchiffrement à une échelle qui est plus large. Mais ça ne va pas poser un problème. Pourquoi? Si on y arrive, ça va pas poser un problème parce que pour casser la cryptographie classique, on a besoin de quelque chose de plus puissant. Mais pour casser la cryptographie quantique, on a besoin de changer les lois de l'univers. Donc c'est pas pour demain. Alors, concernant la deuxième question, euh, je pense que la réponse réside dans la première réponse, c'est que étant donné la façon avec laquelle on se base sur les lois de la nature pour pouvoir effectuer le chiffrement et l'envoi de la clé, il n'y a pas de risque. En fait, il n'y a pas de risque dans ce sens-là. Le risque résiduel réside surtout dans l'utilisation d'équipements classiques d'un autre côté qui peuvent être vulnérables, qui peuvent présenter d'autres types de vulnérabilité. Et donc, ce sont les choses auxquelles on doit vraiment faire attention. Est-ce qu'il y a d'autres questions?
Parfait, merci monsieur.
Je vous en prie.
Je pense que tout était assez clair. Du coup, je vous remercie pour votre présence et j'espère pouvoir échanger avec vous très bientôt par rapport à ces points en particulier parce que ça m'intéresse personnellement.
Je vous en prie, je vous remercie tous de votre présence et j'espère pouvoir vous revoir très bientôt.
Merci. À la revoyure.
Bonne journée. Au revoir.